All right, so gas laws. Before we kind of get into what actual gas laws are, we need to talk about the units that go with these problems, okay? In gas laws, essentially what we're looking at is the relationship between the pressure, the volume, and the temperature of gases, okay? If things get heated up, what's going to happen to the gas? If things are pressurized, what happens to the gas? So on and so on and so on, right? Volume, temperature, pressure are really kind of the relationships we are examining. And so there's a couple different ways we can measure each of these things, right? Volume is most of the time going to be measured in liters. Temperature, what do we usually measure temperature in with science? Celsius, or do you remember another unit for temperature? Kelvin, right? Or Kelvin. And so really with our gas laws, Kelvin is going to be our unit of choice. And then pressure, does anyone know a unit for pressure? These are a little more, or a little less common. PSI, good. PSI we see, where do we see that normally? In tires, right? We usually see PSI in tires. In science, we like to measure pressure in what's called atmospheres, okay? And so we're going to look at the conversions for all of these different units so we can have them in what we want. So we're going to start with something called STP. STP just stands for standard temperature and pressure. And so STP is a set of conditions. Okay, if we say a gas has a volume of 10 liters at STP, that means under these conditions, which is, let's see, Kelvin and, I'm getting ahead of myself here, sorry, I didn't realize I didn't have these in the right order. Okay, if we're talking about temperature, we're going to have a temperature of 273 Kelvin. That is considered standard temperature. But essentially what we're looking at here is anytime we use temperature, we want our unit to be Kelvin. Okay, we want our unit to be Kelvin. And it's not degrees Kelvin. It's just Kelvin, right? I don't know why I don't make the rules, but it's just called Kelvin. So if we want our temperatures to be in Kelvin, we would take whatever temperature they gave us in Celsius, and we add 273 to that to get it into Kelvin. And so that means if I was said a gas is at 100 degrees Celsius, what would that temperature be in Kelvin? 373 Kelvin, right? I just add my Celsius temperature to 273, and that would give me my Kelvin temperature. Okay, so that's a really important conversion we have to do in all of our gas law problems, is to put it into Kelvin. I've got the conversion here to go from Fahrenheit to Celsius. That's not something I think we'll need to really know. You can have it down, but it's not a conversion that you'll need to memorize or that we'll use all that often, right? We want our temperature to be in Celsius, or we'll be given in Celsius most of the time if we're not given in Kelvin. Okay, so our standard temperature unit has to be in Kelvin. Our pressure unit is going to be atmospheres, okay? Or it's abbreviated ATM. Whatever. Okay, pressure's measured in atmospheres. And then we've got a bunch of different ways we can convert things to atmospheres, because we already talked about pressure could be measured in PSI. There's a couple other different units we could. Okay, so if we're looking at our pressure conversions, the first one is the second most popular scientific unit, and it's called a kilopascal. Kilopascal is a pressure unit. And so all of our conversions are set up to equal 1 atmosphere. Okay, we want our units in atmospheres most of the time. So we say 1 atmosphere equals 101.325 kilopascals. These are ones that I would go ahead and write down and highlight them or star them, because pressure conversions are ones we're going to have to do pretty often. Okay, so know where those are at in your notes. So that's one way we can convert to atmospheres. The second one is with something called millimeters of mercury. mmHg stands for millimeters of mercury, right? The atomic symbol for mercury is Hg. Okay? Has anyone have any idea about where this pressure unit would come into play? Millimeters of mercury. This is used when measuring atmospheric pressure, so in a barometer. Barometers are the tools that measure atmospheric pressure. And so when we say millimeters of mercury, what happens is there's actually a physical column of mercury, similar to like a thermometer, and they're just literally measuring the height of that column. right? The more pressure, the difference, the higher that column gets, the less pressure, the lower that column gets, right? It's just talking about how tall that column actually is. And so standard pressure is 1 atmosphere. So if we're feeling just standard pressure, that column would be at a height of 760 millimeters of mercury. Okay, not one we see super often. Okay, torr is similar to millimeters of mercury, not one we use super often, but it would be okay for you to have it down. And then the last one is PSI. Okay, so 1 atmosphere is equal to, I don't know why I lost my equal sign there, equal to 14.7 PSI. And we said PSI is typically found in tires. Do you know what it stands for? Almost pounds per square inch. Pounds of force over the area of the tire, right? Pounds per square inch. That's what pressure is the amount of force applied over a certain area. So PSI is really only an American unit, right? No other countries use pounds or inches. So it's really just kind of an American unit for pressure. So the reason we don't use it is because we want it to be universal. Okay, so our pressure unit is most likely going to be atmospheres. That's what we want it in. So if I had, if I said I had a pressure of 830 millimeters of mercury and I wanted to get it to atmospheres, all I do is convert by saying millimeters of mercury to atmospheres, and I know 1 atmosphere is equal to 760, right? I'm just doing a basic conversion to get it from millimeters of mercury to atmospheres. Does that kind of make sense? And you're just going to divide by that 760 and get, I don't know, a little over 1 atmosphere. We feel okay about those conversions? We should be plenty versed in unit conversions by now. Okay, so here is our actual STP values. If I say something is happening at STP, that means we have a temperature of 273 Kelvin and a pressure of 1 atmosphere. Okay, these are equal. And these are equal, but these are the units we like. Okay, so STP is 273 Kelvin and 1 atmosphere. I would write those down because that's going to come up in problems, right? It might say it has a volume of 10 liters at STP. So now I know the volume and I know the pressure and I know the temperature just based on the conditions that are STP. Okay, stands for standard temperature and pressure. All this means is that it's STP at 0 degrees and 1 atmosphere, or 273 and 101.325. But these two are the same, right? And these two are the same. So we just pick the units we like. We like Kelvin and we like atmosphere. So that's what we consider our STP conditions. Either way, it's the same, right? 0 degrees and 273 Kelvin are the same. 1 atmosphere and 101.325 kilopascals are the same. So this is our temperature condition and this is our pressure condition. But it's just easier to memorize if we already have them in the units we want. Okay? All right. We're going to start talking about 3 different gas laws. You don't have to write this part down right yet. I'm just going to introduce kind of those 3 different gas laws we're going to look at. Boyles Law, Charles Law, and Guy-Lussac's Law are the 3 we're going to look at. They each show us a different relationship between volume, temperature, and pressure, right? That's what we're really examining, is the relationship between volume, temperature, and pressure in gases specifically. So we're going to start with Boyles Law. Okay, Boyles Law. This is looking at the relationship between the pressure and the volume of a gas. Pressure and volume of gas, it says they are inversely related. Bless you. Which essentially just means when one goes up, the other goes down. Bless you. Okay, when one goes up, the other goes down. Remember, we can make these shortened notes. We don't have to take them word for word. The times in which this is true, when we're looking at this being true, if pressure goes up, volume goes down, that the only time that can be true is if temperature is held constant and the amount of substance we have is held constant. So What that means is that if my volume goes down, let's think about a container and I shrink my volume down. What do you think is going to happen to the pressure of the molecules in that container? It's going to go up, right? The closer they have to be, that means the more they're going to bump into each other and the more they're going to bump into the sides of the container. And when molecules collide with the sides of the container, that's what we consider pressure, right? The more that those molecules are colliding with the side of that container, that's what pressure is. And so if our volume goes up, if we expand our volume, does that mean that molecules are going to run into the side of the container more often or less often? Less, which means our pressure goes down, right? If volume goes up, those molecules have more room and therefore are going to collide less, right? So our pressure will go down there. So here is our equation for Boyles Law. P1V1 equals P2V2. Okay? Here's what the variables mean, but I don't think you need to write those out. I think you can probably understand those on your own. P obviously stands for pressure. V obviously stands for volume. And then the 1 and the 2 just correspond to like initial and final, right? P1 is its initial pressure. V1 is its initial volume. P2 and V2 are final pressure and volume. So in these problems, we're going to see a change in what's happening with the gas. Okay, let's go ahead and try one here. 1 liter of gas at STP is compressed to 473 milliliters. What is the final pressure? Okay, a liter of gas at STP is compressed to 473 milliliters. What is the final pressure? Okay, so I'll kind of walk you through how I would look at this and solve this. I'm going to start identifying what variables I do have. Right, I'm going to kind of make myself a list of what I have and what I need. Okay, 1 liter of gas. Tell me what variable does that correspond to?
Volume.
It's volume. And is it volume 1 or volume 2?
Volume 1.
Volume 1, right? My initial volume is 1 liter. Okay, it says my initial gas is at STP. So that means my initial pressure is what? What's my condition for STP for pressure?
Pressure is 1 atm.
Right, it's just one atmosphere. Just 1 atmosphere. It also tells me it's at STP, so I know my temperature here. But is there a change in my temperature?
No.
And does it ask me anything about a final temperature? So I can just leave it off, right? I'm assuming that temperature is staying constant. Okay? However, it says it's compressed to 473 milliliters. What variable does that correspond to?
V2.
Final volume. But do you see an issue?
It's milliliters.
Yeah, very good. Our units have to be consistent. And here I have milliliters. Over here I have liters. So I'm just going to go ahead and change it to liters since that's what I had initially, right? You could pick to have them both in milliliters. That would be fine, but I've already got liters written down. So I'm just going to move this from 473 mils to 0.473 liters, right? There's 1,000 milliliters in a liter. So it's just divide by 1,000. Are we good with that conversion? That should be something we feel pretty good about. Then it says, what is my final pressure? So that means P2. Do I know P2? No, I put a question mark there so I can really hone in on what I'm solving for, right? I don't know my P2, so that's what I'm going to solve for, okay? And now I just plug it in, okay? So P1 is 1 atmosphere, V1 is 1 liter, equals P2, which I don't know, times V2, which is 0.473. Okay, so how do I get P2 by itself? All I do is divide over 0.473. That cancels. Divide over 0.473. And so that means I'm just taking 1 divided by 0.473. And I'm getting a final pressure of 2.11. And then what would my units be? Atmospheres. Okay, so then I check, is my answer rational? Does it make sense? What did my volume do? It went down, so my pressure should increase. And did it?
Yeah.
It went from 1 atmosphere to 2.1. So at least it makes sense. It's in the realm. As long as I did the math right? We have an answer that does make sense there. If I have 5.6 liters of a gas in a piston at a pressure of 1.5 atmospheres, and I compress the gas until it is a volume of 4.8 liters, what will the final pressure be? Okay, I have a 5.6 liters of a gas with a pressure of 1.5. I compress the gas until it's got a volume of 4.8. What will the final pressure be? So this problem feels really similar to the one we just did, right? 5.6 liters. Is it a pressure or a volume? It's volume. And is it V1 or V2? 1, right? That's my initial. How did I know that it was volume? It's based on the unit. We've got to feel good about picking out the variable based on the unit itself. Okay, I've got a pressure of 1.5 atmospheres, so that means that's got to be P1. It's compressed until it has a volume of 4.8, so that means V2 is equal to 4.8 liters, and P2 is what I'm solving for. Right? I think making the list is really going to be important until we feel really comfortable with these gas law problems. So please try to make that a priority. Then when I go plug it in, it's P1 times V1. Oops. Equals P2 times V2. And so now I'm going to want P2 by itself. So I need to divide 4.8 liters to the other side. And I'm going to run the math, right? Multiply the top, divide by the bottom. Okay, I got my final pressure at 1.75 atmospheres. The important thing with these gas laws is that your units need to be consistent on both sides. If they would have both been measured in PSI instead of atmospheres, that would have been okay as long as they were consistent. The only unit that must be converted is temperature. That's the only one that has to be in Kelvin. Otherwise, we could survive as long as they were the same on both sides. Okay, so if they were both milliliters, fine. Both millimeters of mercury, fine. Okay, Charles' law is looking at volume and temperature. They're directly related. So that means if one goes up, what's the other one do? It goes up. One goes up, the other goes up. If one goes up, the other goes up. So it generally looks like a pretty straight line on the graph. They have a direct relationship. So we'll see that increase happen. Here is our equation right here. V1 over T1 equals V2 over T2. Okay? Direct relationship here. One increases, the other increases. I have 67 liters of helium in a balloon at 28 degrees Celsius. And I increase the temperature of the balloon to be 47 degrees Celsius. What will the final volume of the balloon be?
So we have to transfer Kelvin.
Yeah, we need our temperatures to be in Kelvin. They have to be. That's the only unit that really has to make a change. Okay, if I have 67 liters of helium in a balloon at 28 degrees Celsius and I increase the temperature to 47, what will the final volume be? So let's start looking at the numbers we have. 67 liters, what variable do you think that is? V1, right? It's volume and it's the initial volume. So 67 liters. 28 degrees Celsius is my initial temperature, but I don't want it in Celsius. I want it in Kelvin. So I'm going to take 28 plus 273 and get that into Kelvin. Make sure you have your calculator out if you don't yet. You need to be doing these along with me. Okay, 301 Kelvin is my initial temperature there. Then it's my V2. Do I have a V2? No, that's what I'm solving for, because it asks literally, what will the final volume be? Write your question mark out so you really know what you're looking for. My final temperature, it says, was 47, but can I leave it at 47? No, I'm going to add 273. I'm going to get it into Kelvin, and that gives me 320 Kelvin. Okay, and then we're going to plug it in. That's it. Right? Gas laws are really simple in terms of the algebra that goes with them. So 67 liters over 301 Kelvin equals V2 over 320 Kelvin. Okay, do you know how to solve proportions like this?
Yeah,
Cross multiply and divide. So if I'm solving for V2, I'm going to cross multiply and then divide. Right? Is that how you guys were taught that algebra? Or not so much?
It was, you have to multiply by the bottom.
320 times 67 divided by 301. Are we expecting our volume to increase here or decrease? We're expecting an increase because we know they're directly related and our temperature went up. So V2 should be 71.2 liters. Relationship, pressure and temperature. Pressure and temperature. If they're directly related, what's that mean as one goes up? The other one also goes up, right? Okay, sorry. Okay, there's our equation for Guy-Lussac's law, and then we're going to try that problem listed right underneath there. Determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees Celsius to 30 degrees Celsius. So if my volume is constant and my temperature increases, what does that mean about my molecules? Are they going to be moving faster or slower? A temperature increase means molecules are going to do what? They're going to move faster, which means they're going to run into the walls of the container more, which is going to be an increase in pressure, right? So that's why those two are related. Pressure change when 1 atmosphere of pressure. So that means that's P1. My temperature initial is not 20, but 293, right? 273 plus 20. P2 is what I'm solving for, and T2 is 30 plus 273, which is 303. So I'll take 1 atmosphere over 293 equals P2 over 303. And the same thing is going to be true here. We just cross multiply and then divide. Cross multiply diagonally and then divide by the leftover one. And so I got a slight pressure increase, and I got P2 equal to 1.03 atmospheres. All right, we did not see a very big temperature increase, so it should make sense to us that we don't have a very big pressure increase either.